Hello, hello. Am I audible to everyone? Good morning, please. Is my voice coming to you? Tell me. I am audible, visible. Good morning, Durga. Good morning, Blessy. Okay, Durga. Very good, very good, very good. Ananya, very good. Okay. So what we were covering in previous class, I think we have started units and dimension. Good morning, Zamir. Good morning. Units and dimensions. We were doing units and dimension. We were learning about units and dimension. Is this clear? So in the previous class, we have discussed about the unit portion. Unit is the basis with help of which we measure a physical quantity. Units are in our SI system, the international SI system. We have defined that 7 quantities are fundamental, and all other quantities are dependent on 7. Besides the 7 quantities, there are 2 more complementary quantities. We have defined the units of the 7 physical quantities, and with help of these units, we can derive units of all other quantities. Units of all other quantity. For example, unit of force. Unit of force. Force is having unit Newton, which is nothing but 1 kilogram meter per second square. 1 kilogram meter per second square. So kilogram, meter, second, these all are units of length, mass, and time. So using the units of basic or fundamental physical quantity, we can define unit of any other derived quantity. Okay, we have covered units in the last class. SI system we have covered. Okay, and today we are going to start dimensions portion. Today we are going to start dimensions. In the previous class, we have discussed about physical quantities. Physical quantities are of 2 types: fundamental and derived. Fundamental and derived. Fundamental physical quantities are those which are not dependent on other physical quantities. Their definition is itself complete. They do not depend on any other physical quantity for their definition. For example, if we talk about temperature is measure of degree of hotness or coldness of a body. We are not using any other physical quantity to define temperature. But if I ask you what is speed, speed is distance traveled by time taken. Here I am taking help of distance and time, which are 2 fundamental physical quantity to define speed. So if you define any derived quantity, you require the assistance or help of the fundamental physical quantity. So all the derived quantities are dependent in some way on the fundamental physical quantity, and fundamental physical quantities are not dependent on any other physical quantity. Was this clear? What are fundamental physical quantities? What are derived physical quantities? We have covered in this previous class. Okay. There were 7 fundamental quantities. 7 fundamental quantities SI system, which are mass, length, time, current, temperature, amount of substance, and 7th, luminous intensity. For these 7 fundamental physical quantities, we have defined their units. Okay. Now today we are starting dimensions. What are dimensions? Our derived quantities are dependent on fundamental physical quantity. The definition itself involves some fundamental physical quantity. So in what way they are dependent on fundamental physical quantities, that is given by dimensions. Write down, dimensions are the powers. What are dimensions? Dimensions are the powers on which a derived quantity is dependent with fundamental physical quantity. Dimensions are powers of fundamental physical quantities on which a derived physical quantity is dependent. These are powers of fundamental physical quantity. For example, it's better to go with example. If I write down speed, speed is defined as distance traveled by time taken. Speed is defined as distance traveled by time taken. What is the dimensions of distance? Distance, we use symbol L to represent distance. We use symbol T to represent time. Hence, we can say the speed is dependent on length and time. This is a way to show that speed is dependent on length and time. This is a way to show speed, length and time. So we will say that speed is having dimension 1 in length, dimension -1 in time. Speed is dependent on distance and time. It is proportional to distance. It is inversely proportional to time. So speed is dependent on our fundamental physical quantities. And what are the powers of fundamental physical quantities on which the speed is dependent? These powers are called dimensions. These powers are called dimensions. Here, the power length 1 and power t minus 1. These are showing the dimensions of speed. We will say the dimensions of speed is 1 in length, power of length is 1, and -1 in time. Okay, so powers of the fundamental physical quantities on which a derived quantity is dependent, they are called dimensions. And we are using some symbols to show the dependency on the fundamental physical quantity. For mass, I will use a symbol M. For length, we use L. For time, we use T. For current, generally A is used. For temperature, K, and some books also uses theta. In some questions or some book may use theta. Amount of substance, usually I write by mole. Luminous intensity by candela. Luminous intensity is not in our syllabus. No question will be asked regarding this. So that's why we will require these 6 physical quantities predominantly. Okay, but we should know what is the symbol for candela. So these are the symbols we will use to represent the powers of fundamental physical quantity on which a derived quantity is dependent. So what are dimensions? Dimension shows the dependency of a derived physical quantity on fundamental physical quantity. Is this point clear till this point? Tell me. What are dimensions? We are just discussing dimensions. Dimensions are the powers of physical quantities, fundamental physical quantities on which a derived quantity is dependent. So it's a way to express the dependency of derived quantity on fundamental quantity. Okay. Now, so we have discussed about what is the different symbol we will use for different fundamental physical quantity, and this is a way of writing dimension. Whenever we want to write dimensions of any physical quantity, we will enclose that physical quantity in brackets. If I enclose the physical quantity in square bracket, it means I am showing dimension. It means I am showing dimension. I am showing dimensions. So whenever a physical quantity is enclosed in square bracket, I am showing its dimension. And how dimensions is shown? It is represented like this. It is represented like this. The symbols will be used for the fundamental physical quantities, and there will be powers. This complete expression, like here, I am writing speed is equal to LT minus 1. It means I am showing dimensions of speed. Square bracket means I am showing dimensions of speed, and that is LT minus 1. So this kind of equation in which on one side we are writing some physical quantity with square bracket, on other side we are writing the dimensions. This is called dimensional formula. Dimensional formula. This expression is called dimensional formula, and this equation is called dimensional equation, because there is equation, there is a sign of sign of equate here. So that's why this is becoming an equation. This is called dimensional equation. What is dimensional formula? It's a formula showing dimensions. What is dimensional formula? It's a formula showing dimension. What is a dimensional equation? It's an equation having equal sign in between. It is an equation showing the dimensions. Is this point clear? The meaning of dimensional formula, the meaning of equation, dimensional equation. Just writing equal, we are getting dimensional equation. This formula is called dimensional formula. Okay. So what are dimensions? Dimensions are the powers of fundamental physical quantity on which a derived quantity is dependent. Let us, for example, find out some more dimensions. Some more example. Let us write more example. Let's say I am finding dimensions of velocity. Velocity, dimensions of velocity. How velocity is defined? When I am writing square bracket, it means I am writing dimensions. How velocity is defined? Velocity is defined as displacement by time taken. And displacement is just like a length, na? It's also measured in length. So the symbol for showing length is L and symbol for showing time is T. I am writing dimensions of displacement which is L, dimensions of time which is T. This is again LT minus 1. This is again LT minus 1. So speed, which was a scalar, and velocity, which is a vector. Scalar and vector are not equal quantities. They are different quantities. One is a vector, one is scalar. But their dimensions are equal, LT minus 1. The dimensions are equal. We can have equal dimensions of different physical quantities. See, they are very different. One is vector, one is scalar. They are different physical quantities. But we may have equal dimensions. There are many pairs of physical quantities having equal dimensions. AC is cooling very low. Just a minute. Okay. So there may be equal dimensions of different physical quantities. This is an example. There are many more examples. Okay. Let us find some more dimensions. Let us find dimensions of momentum. Momentum is defined as mass into velocity. What is the dimensions of momentum? Momentum is represented by P vector. It will be dimensions of mass. Mass is represented by symbol M. Dimensions of velocity, which is LT minus 1. This will be MLT minus 1. In this way, we can find out many dimensions. Acceleration. Acceleration, which is change in velocity upon time taken. Change in velocity will also be having dimensions of velocity. So it is LT minus 1. We have just calculated it earlier. Divided by time. LT minus 2. Dimensions of acceleration, LT minus 2. Dimensions of force. Newton's second law, remember, mass into acceleration gives you force. So dimensions of force will be mass into dimensions of acceleration, LT minus 2. So there are different physical quantities that we can find out dimensions in this way. We just need to know the formula of physical quantity to find out the dimensions. I should be able to represent the physical quantity in terms of other physical quantity for which I know the dimensions. Okay, if I can do this, I can find out the dimensions. For one more example, we can do fifth, torque, which is R cross F. So dimensions of torque vector, it will be dimensions of R. R is length, and force, which is MLT minus 2. This will be ML square T minus 2. Dimensions of torque. Dimensions of energy. Energy may be potential energy, kinetic energy, heat energy. All kind of energy have same dimensions. All kind of energy. Energy, all kind. So energy, kinetic energy, we can take an example. So dimensions of energy or dimensions of kinetic energy all are same. That kinetic energy is defined as half mv square. Half mv square. So half will not have any dimension. Number do not have any dimensions. Okay. Numbers. If you have pure numbers, they do not have any dimension. Dimensions of mass m. Dimensions of velocity LT minus 1. Square of that. dimension of mass, dimension of velocity. So ml square t minus 2. ml square t minus 2. If you observe here, torque and energy have same dimension. Torque and energy have same dimension. Torque and energy. Yeah, work is also same. Work and energy is also same. Work can be converted into energy. Energy is a form of work. Okay, energy is changed when I am doing work. Okay, so work is also energy. This is also work. Work or energy which is scalar is in same dimension as a vector quantity which is torque. See, two different physical quantities may have same dimension. Okay, we can have many examples. 7. Angular momentum. Angular momentum. Angular momentum, sometimes it is represented by L vector. It is R cross momentum vector. R cross momentum vector. So dimensions of angular momentum will be dimensions of length. Dimensions of momentum was mlt minus 1. So ml square t minus 1. Dimensions of angular momentum. Dimensions of Planck constant. Planck constant. Planck constant H. Do we remember any formula regarding Planck constant? Yes, energy of photon is given by h nu. Some people also say this is hf. Nu or f is same thing. This is frequency. Dimensions of frequency. How to find dimensions of frequency? It is 1 upon time period. So it's t minus 1. Dimensions of frequency t minus 1. So you can put it here to find dimensions of h. It will be dimensions of energy upon dimensions of frequency. Dimensions of energy is ml square t minus 2 upon t minus 1. So it will be ml square t minus 1. Yes. So this is dimensions of Planck constant. Why I am calculating dimensions of Planck constant? To show you that, see, these two dimensions are same. Planck constant, which is just a constant used for energy of photon, it is having same dimensions of a vector, which is angular momentum. So scalar and vector here also have same dimension, and they two are different physical quantities. Planck constant and angular momentum have same dimension. Planck constant and angular momentum have same dimensions. Planck constant and angular momentum have same dimension. Okay. Planck constant and angular momentum have same dimension. So different physical quantities may be having same dimensions. Everything is clear till this point. I am calculating dimensions of different physical quantities. Yes. Okay. We will calculate some more dimensions. Pressure, stress, strain. Okay. But before that, let us write some important relations. Let us write some important points. First point, what is dimensionless quantity? What is dimensionless quantity? There are many physical quantities which are, yes, we will write dimension of thermal conductivity, etc. But first, we will cover some basic points. What is dimensionless quantity? A physical quantity which do not have any dimension. Its dimension is 0, 0, 0. Powers of fundamental quantities is 0, 0, 0. That is called dimensionless quantity. There are many examples of dimensionless quantity, like angle. Angle is defined by arc length and radius. It's a ratio. Angle, dimensions of angle will be dimensions of arc length, which is L, dimensions of radius, which is also L. So it is L to the power 0. L by L cancel out, L to the power 0. There are many examples of dimensionless quantity. Solid angle. Solid angle is also dimensionless. Solid angle is defined by area by radius square. So it's again dimensionless. Okay. Refractive index. Strain. Dimensionless. Coefficient of friction. coefficient of restitution. Coefficient of restitution is dimensionless. Then thermal in Wien-Stefan law, we find emissivity. Okay, that is dimensionless. I am not asking emissive power. Emissivity is dimensionless. Emissivity is generally generated by small e or epsilon naught. Emissivity. This is dimensionless. Then displacement gradient. What is emissivity? You must be knowing that a total emissive power of a gray body is sigma E A t to the power 4. This is total emissive power. That is dq by dt. Energy radiated per unit time. Sigma E t to the power 4. Here, this small e, which is also sometimes denoted by epsilon, this is emissivity. This is dimensionless. This emissivity is dimensionless. Okay. Coefficient of friction. Yes. Coefficient of restitution, displacement gradient. There are many physical quantities which are dimensionless. Out of this, all physical quantities which are dimensionless, all do not have any unit. Others do not have any unit. Only these two also have unit. So this all are dimensionless, but out of this do not have any unit. This do not have any unit, but this has unit. So not all the dimensionless quantities are unitless. There are two dimensionless quantities which have unit, but other dimensionless quantities are unitless, and all the unitless quantities are dimensionless. All the unitless quantities are dimensionless. Okay. So what is a physical quantity which is dimensionless? Which is having dimensions of fundamental physical quantities as 0, 0, 0. If you divide to same kind of physical quantities, you will get dimensionless physical quantities. So in this all situations, actually we are dividing same kind of physical quantities. Angle is arc length by length, arc length by radius, area by radius square. Same type of physical quantity we are dividing. Refractive index is speed of light in free space divided by speed of light in medium. So it's just a ratio of same type of physical quantity. Strain is change in length upon original length. This is again a ratio. Coefficient of friction, it is a value of friction upon normal force. This is again a ratio. Coefficient of restitution, velocity of approach upon separation, separation upon approach, separation upon approach. So it's also a ratio. Emissivity, this is ratio of emissive power of gray body divided by emissive power of black body. It's a ratio of emissive power. So again, this is dimensionless. Displacement gradient is change in displacement upon change in position. Ratio of same kind of physical quantity, it's dimensionless. So whenever we have ratio of same kind of physical quantity, we will get a dimensionless physical quantity. Till this, everything clear? Any doubt? Okay, very good. Now we will write some rules of dimensions. Some rules of dimension. Some rules of dimensions. There is no meaning of equating or adding two different physical quantities. I cannot add volume with mass. Volume with mass is meaningless thing. Similarly, I cannot add height with area. Two different physical quantities cannot be added. Force plus momentum is nothing. Torque plus energy is again nothing, because torque and energy are having two different physical quantities. They are two different. Torque is a vector, energy is scalar, so they cannot be equated. So two different physical quantities cannot be equated, but they can be equated if they are same. If they are same, their dimension must be same. Okay, so write this down. We can add, subtract, or equate. We can add, subtract, or equate only same physical quantities. Same physical quantity. Okay, we can add, subtract, or equate only same physical quantities. If they are same, their dimensions must be same. It means dimensions same. So it's also can be written like we can add, subtract, or equate same physical quantities of same dimensions. Physical quantities of same dimension, but this is not a complete sentence, na? Because I can, in that way, I can equate torque with energy. Torque and energy have same dimension, but these are different physical quantities. Actually, I cannot equate them. But if I write, I can equate physical quantities of same dimension, then that statement becomes wrong. Okay, I can equate same type of physical quantities, but I cannot equate a vector with scalar. Okay. If in some question, based on this rule, I am giving you a question like alpha is equal to beta plus gamma. This is a question. Alpha is given as, this is given, and dimensions of beta is MLT minus 1. I am giving you dimensions of beta. Find dimensions of alpha and dimensions of gamma. Whenever we write a quantity in square bracket, it means we are asking dimensions. So dimensions of beta is given, and I'm asking dimensions of alpha and gamma. Difference type means we can multiply. The second rule, wait for that. In second rule, I will write that. Alpha is given as beta plus gamma. Alpha is given as beta plus gamma. Given, it is given to you that alpha is equal to beta plus gamma. And beta is MLT minus 1. Beta is MLT minus 1. Find dimensions of alpha and gamma. Find dimensions of alpha and gamma. So we can add only those physical quantities which are having same dimensions. We can equate only those physical quantities which are having same dimensions. So in solution, I may write alpha, beta and gamma. I am adding beta and gamma, so they must be having same dimension. I am equating alpha and beta, so again they must be having same dimension. So all have same dimensions as they are equated and added. I can equate, add, subtract only the physical quantities which are having same dimensions. It means I already know dimensions of beta. So dimensions of alpha and dimensions of gamma, that must be equal to MLT minus 1. MLT minus 1. Yes. I can add, subtract or equate only those physical quantities which have same dimensions. Let us go to next property, next rule. Rule number 2. Rule number 2. Rule number 2. I can multiply or divide different physical quantities. That can we do. We can multiply or divide two different physical quantities. Okay, two different physical quantities. Like for example, pressure is defined as force by area. Force and area are different physical quantity, but I am dividing them to find pressure. Okay, if anyone asks you what is the dimension of pressure, that will be dimensions of force, MLT minus 2 divided by area, which is L square. So it will be ML minus 1 T minus 2. And stress also has same dimension. Stress is also having dimensions of pressure. Also all kind of Young's modulus, bulk modulus, Young's modulus, bulk modulus, modulus of rigidity, all kind of modulus of elasticity, all kind of modulus of elasticity, they are stressed by strain. Strain is dimensionless, so they will have dimensions of stress only. They will have dimensions of stress only. Okay. Young's modulus, bulk modulus, modulus of rigidity, all kind of modulus of elasticity, they are having same dimension of stress and pressure. All these have same dimensions. Okay, so second rule is we can multiply or divide two different physical quantities. That is okay, but we cannot equate or add or subtract two different physical quantities. Okay, so Kusuma, your doubt is clear? I hope so. Third, Third rule. Trigonometric ratios, powers, exponent, logarithm, all are dimensionless. Angle, trigonometric ratio, exponential, powers, log, all are dimensionless. All are dimensionless. Sin theta, cos theta, tan theta, these represent the ratio of two sides of triangle. They represent ratio of same physical quantities. Sin theta is perpendicular by hypotenuse, so it should be dimensionless because it's ratio of same type of physical quantity. Same type of physical quantity. Dimensions of sine, cos, tan, sec, cosec, cot. This will be 0, 0, 0. Dimensionless. In the angle also, this theta also dimensionless. Theta is dimensionless. Whenever you are writing sine of anything, that anything should be dimensionless because sine is only defined for angles. So sine of theta, theta is dimensionless. Log is dimensionless. E to the power x is dimensionless. Dimensions of e to the power x is nothing. Dimensions of log of x is nothing. They are dimensionless. Dimensions of sine, cos, nothing. Dimensions of any number to the power anything, nothing. Dimensions of any number to power anything, nothing. Okay, in these expressions, the x which is power on, which is either in power, which is in log, which is in power, these are also dimensionless. In this expression, x is also dimensionless. X is also dimensionless. Okay, suppose I write e to the power theta, then this theta must be dimensionless. Powers are dimensionless. Whenever you write any number to power anything, powers are dimensionless. Is this clear? Third property. Trigonometric ratios, log, exponents, powers, all these are dimensionless. All these are dimensionless. Yes. Naga has given me a good example. Relative permittivity, relative permeability, these are also dimensionless. They are ratio. Relative permittivity, relative permeability, these are also ratio. They are also dimensionless. Very good, Naga. Okay. All the powers are dimensionless. So we can solve some question based on these rules. We can solve some question based on this rule. Okay. Let us solve some question. Wave equation y equal to a sine omega t minus kx is equation of y, which is displacement, t which is time, and x which is position. Okay, I am giving you a equation. Give me dimensions of a, dimensions of omega, and dimensions of k. Here a is called amplitude, omega is called angular frequency, and k is called wave number. Wave number. Okay. So I am giving you wave equation, which is y equal to a sine omega t minus kx. This is wave equation. If this is wave equation where y is displacement, t is time, x is position, give me the dimensions of a, omega, and k. Try to solve this. We will use our rules to find answer of this question. Amplitude is L. Very good, Durga. Find dimensions of a, omega, k. Dimensions of amplitude, angular frequency, and wave number. No, Durga. Sorry, you are wrong. Take a minute. Try to solve this. Find me dimensions of A, omega, and K. Okay, very good. No, wave number is wrong. Yes, Sahiti, very good. Yes. Okay, let me help you. See, y is equated with a and sine of this. Sine of this should be dimensionless. Sine of any expression is dimensionless. So because sine is dimensionless, y and a must be having same dimension. Solution. Dimensions of a must be equal to dimensions of y. Because sine do not have any dimension, so the dimension should be equal. Y is displacement, so dimension should be L. Y is displacement, so dimension should be L. And within sine, whatever we are writing in sine, which is omega t minus kx, that is an angle. That is an angle. So it should be dimensionless. It should be dimensionless. This complete expression is dimensionless, but I can add or subtract physical quantities of same dimension. If this complete expression is dimensionless, then omega t and kx are also dimensionless. Omega t and kx are dimensionless. Because their difference is dimensionless now, so they must be dimensionless. Omega t is dimensionless. Omega t is dimensionless. That can only be possible when omega and t are having inverse dimension. Omega and t are having inverse dimension. So dimensions of omega should be dimensions of 1 upon k. Sorry. Dimensions of omega should be equal to dimensions of 1 upon t. Omega into t is dimensionless. Omega into t is dimensionless. It means dimensions of omega and dimensions of t, when they are product, when they are multiplied, we are getting dimensionless thing, which is 1. So they should have inverse dimension. Whenever product of two physical quantities is dimensionless, they should have inverse dimension. Whenever whenever ratio of two physical quantities is dimensionless, they should have same dimension. Here the product is dimensionless, so their dimension must be inverse of each other. Inverse of each other. And what is dimensions of t? T is time. In question it was written time, so it should be t to the power minus 1. Similarly, kx is dimensionless. So dimensions of k should be dimensions of 1 upon x. X was position, length, L minus 1. So correct answer will be amplitude is having dimensions of L, omega dimensions of t inverse, k dimensions of L inverse. Wave number is having dimension L inverse. Wave number is having dimensions L inverse. Is this question clear? Anything written in sine is dimensionless. Omega t minus kx is dimensionless. For that to be, omega t and kx both should be dimensionless. Both should be dimensionless. Omega t and kx both are dimensionless. For that, omega and t should have inverse dimensions. K and x should have inverse dimension. Clear? Let us solve some more question. If P, which is pressure, is given by P naught e to the power minus alpha x square in a gas column. In a gas column, pressure is given by P naught e to the power minus alpha x square, where x is position. Find dimensions of P naught and dimensions of alpha. Find me dimensions of P naught and dimensions of alpha. Try to solve this. P is pressure in a gas column. Pressure in a gas column is given by this expression, P naught e to the power minus alpha x square. Now tell me the dimensions of P naught and P naught and alpha. So dimensions of P, which is pressure, and x, which is length, is known to you. Try this. Yes, alpha dimension is correct, Rakesh. Blessy, yes. I'm also asking dimensions of P naught. I'm also asking dimensions of P naught. Give me the dimensions of P naught and alpha. Yes. Pressure, you should be knowing the dimensions of pressure. Pressure was force by area. And P naught should have same dimension. Why? Because alpha, e to the power anything is dimensionless. Exponents are dimensionless. So we know as e to the power anything is dimensionless. It implies that dimensions of P naught should be dimensions of pressure, which is force by area. Force mLT minus 2 by area, L square. So it should be mL minus T minus 2. This is dimensions of P naught. And in power, whatever is written in power, that should also be dimensionless. Alpha into x square is dimensionless. Alpha into x square is dimensionless. So dimensions of alpha must be 1 upon dimensions of x square, that is L to the power minus 2. Answer. Dimensions of alpha should be 1 upon x square, L to the power minus 2. Because alpha into x square is dimensionless, so their dimensions are inverse of each other. Whenever product of two physical quantities is dimensionless, the dimensions are inverse of each other. Okay. Is this point clear? Is this point clear? So we are finding dimensions of some unknown physical quantities by using the rules of dimensions. Everything clear? We can solve one more question. We can solve one more question. If force is equal to alpha t square minus beta t, find dimensions of alpha and dimensions of beta, where t is time. T is time. Force is dependent with time. The equation of force with time is given to you. I am asking you dimensions of alpha and beta, where F is force, T is time. Solve this. Give me dimensions of alpha and beta. If F is force, T is time. Yes, bless you. We can add or subtract or equate physical quantities having same dimensions. We can add, subtract or equate physical quantities having same dimensions. Force alpha t square and beta t should have same dimension. Alpha t square dimension should be equal to dimensions of beta t should be equal to dimensions of force. We are equating force with these two, so dimensions will be equal. Okay, dimensions of force is mLT minus 2. We should know these basic dimensions. Okay, now I know dimensions of beta into t. So dimensions of beta into dimensions of t, which is t, is mLT minus 2. Just use this to find dimensions of beta. It will be mL t and t minus 2, it will be t minus 3. Similarly, now you can find dimensions of alpha also. Dimensions of alpha into dimensions of t square, that is force, mLt minus 2. So dimensions of alpha, mL t to the power minus 4. If you divide t square here, you will get t to the power minus 4. Is this simple? Yes, Hari, Ishwarya. Everything, is this clear? Yes. So we can add, subtract or equate physical quantities of same dimension. But I can multiply and divide two different physical quantities. That is not a problem. Trigonometric ratios, exponents, logarithm, all these are dimensionless. Powers are dimensionless. So we should just remember these basic ideas to find our answers. Okay, is this clear? Okay, very good. Now we will find some more formulas of dimension. Till now we have discussed about some of the formulae. We'll discuss more formulae of the dimensions. Let us go to, we have discussed pressure. Up to pressure we have done. So after pressure, let's say find dimensions of density. Dimensions of density. Dimensions of density. Dimensions of density. Density is mass by volume. Density is mass by volume. Mass is m, volume length cube. The dimensions will be ml to the power minus 3. Okay. Dimensions of charge. Electric charge. Charge is current into time. Charge is current into time. Charge is current into time. Dimensions of current is A. Dimensions of time is T. Dimensions of current is A. Dimensions of time is T. So AT. Dimensions of charge is AT. Very good. Dimensions of universal constant of gravitation. Capital G. Dimensions of universal constant of gravitation. You should be remembering that F equal to G m1 m2 by r square. You should remember this. So G can be written as force into r square divided by m1 m2. To solve this to get dimensions of G. So dimensions of force mlt minus 2 into r square, that is L square. Whole thing divided by product of masses m into m. So if you just rearrange this, m to the power minus 1, L to the power 3 and t to the power minus 2. T to the power minus 2. This is dimension of universal constant of gravitation. Yes. Okay, in this way you can find many more dimensions, like dimensions of epsilon naught, permittivity. Permittivity. You know this force between charges is given by 1 upon 4 pi epsilon naught q1 q2 by r square. q1 q2 by r square. So dimensions of epsilon naught, you can divide F here. So it will be dimensions of q1 q2 by 4 pi f r square. Just by the formula. Q1 and Q2, AT into AT, A square T square. 4 pi do not have any dimension. It is dimensionless number. Constants do not have any dimensions. Numbers do not have any dimensions. Force is mlt to the power minus 2 into r square, which is L square. Just rearrange it. M to the power minus 1. And in denominator I have L cube. So numerator there will be L cube. T to the power 2 and t to the power minus 2 to the power 4 and A square. This is dimensions of epsilon naught. Okay, is this clear? Dimensions of epsilon naught. Yes. So in our gym material, you may find different physical quantities and their dimensions, and we can find out different dimensions just if we just know the formula. For example, to find dimensions of epsilon naught, we should be knowing this formula, permeability. Okay, this is permittivity, not permeability. Permeability is mu naught. It is used in formula in magnetic field. Like we can write down energy in a space, energy density, energy per unit volume. If half 1 upon mu naught b square. This is a formula containing mu naught. Or there is a very easy formula also. Speed of light is 1 upon root over mu naught epsilon naught. I already know dimensions of epsilon naught. So I can find mu naught because I know dimensions of speed. You can write this mu naught and epsilon naught will be 1 upon c square. So dimensions of mu naught is 1 upon c square epsilon naught. So it will be 1 upon dimensions of c square is lt minus 1 square into dimensions of epsilon naught. You can put it here. You will get dimensions of mu naught. Okay, now you can solve this on your own. Clear? Okay. So is this everything clear? Sir, I power minus 3 No, here current to power 2 should be there. No, minus 3. This is correct, I think. Okay, everything clear? L to the power minus 3 should be there. Yes, this is wrong. Yes. L to the power minus 3 should be there. You are saying correct thing. Yes, L to the power minus 3. By mistake, I am writing L to the power 3 there. Okay. So we can find out dimensions of different physical quantity if we just know the formula. Okay. So you will find a table of dimensions formula of different physical quantity in our material. So try to memorize the table. Try to go through the table. And if you don't have material, you can search on the net also. You will find list of dimensions of different physical quantity in many places. Okay. So today we have covered some part of dimension analysis. I have covered what are the dimensions, some rules of the dimensions. In the next class, I will start application of dimension analysis. What are application of dimension analysis? We can convert unit of one physical quantity into other unit. We can convert units using dimension analysis. I can check for correctness of an equation if I know dimensions. An equation will be correct only if it is dimensionally correct. So we can check correctness of an equation. Then we can find out the relationship among different physical quantities. Okay, so this kind of things we will cover in the next class. Okay, so let's meet in next class. I also have another class. So bye, take care, and try to read the dimensions of different physical quantities. Okay, in the next class that will be required. Thank you all of you. Bye, take care.